Hello, this is Lab 6, Reactions, Rates, and Chemical Equilibrium, SCC 110. So we're going to talk about some of the factors that govern a reaction rate. We're going to talk about shifts in equilibrium to the left, to the right. But let's start with the collision theory. It's a theory used to predict the rates of reactions, how effective they are, and it has two factors, the molecular orientation and the activation energy. We'll briefly talk about these two on the next slides. So one of the factors is molecular orientation. So I like to think of it as if you have two reactants coming together, they have to fit in the proper way, like a jigsaw puzzle. So in this case, we have NO2Cl reacting with Cl to give us NO2 plus Cl2. So you can see that the Cl combines with the Cl to give us Cl2. It's a diagram here. The top one here shows that for the reaction to occur, the two Cl's have to come together. So for an effective collision, the reactants have to orient themselves so that the Cl can be transferred to the, can make a bond with the Cl, and the Cl can be transferred over from the NO2Cl. The other factor is the activation energy. So whenever two things collide or two reactants collide, it has to have enough energy. It has to overcome the activation barrier, we like to say. It has to have enough activation energy to reach a transition state, this is a transition state, and then to give our products. So you can think of it as a fence or as a for instance, a basketball hoop, the slam dunk. You can jump with very little energy as many times as you want, but you'll never get to the activation energy. You'll never jump over the fence. What you need is a specific amount of energy that reaches the activation energy, which can then give us our products. So in this case, we have N2 plus O2 giving us 2NO. And if you guys look here, we have a graph of energy versus the reaction. And here we see that the N2s and the O2s again have to combine in a particular manner so that the N2 breaks with the O2 breaks and then to combine to make two NO molecules. If you recall from lab 2, we have here a endothermic reaction. The energy for the reactants is lower than the products. So we need to add energy for this reaction to occur. So the reaction rate is determined by the formula of change in the concentration divided by the change in time. The rate, just like in a car, miles per hour, you can think of it as a rate change in concentration per change in time. And there are three things that can affect this, is the temperature change in concentrations, and presence of a catalyst. So the temperature of a system. So if you increase the temperature of the reaction, the molecules will move faster. If they move faster, you'll have more collisions and a higher probability of finding the correct, you can say, jigsaw puzzle to find the right fit for the reaction to move forward. Example here is if we put food in the fridge, we do this so we can slow down the reaction, because they won't move as fast, they probably won't have the correct activation energy, or lower probability of getting the correct activation energy, and because there's less collisions, there's a less probability of finding the correct fit. If we increase the concentration of the reactants, the collision rates between the two reactants will increase, and therefore there's a greater chance of finding the correct geometry or the correct puzzle fitting, as I say, to get to the activation energy. And the third one is a catalyst, which maybe you've seen in your biology class. And what a catalyst does, it speeds up the reaction. And in terms of our energy versus reaction progress graph, what the catalyst does is it lowers the activation barrier, meaning you need less energy to reach the transition state to give us our products. And in this case, we have a exothermic reaction where the energy of the products is less than the reactants. So the three factors that affect how fast the reaction will go are catalyst, temperature, and concentration of reactants. So let's look at some examples here just to apply what we just learned. If we increase the temperature of a reaction, that will increase the rate of the reaction, because if you increase the temperature, the molecules move faster, therefore a greater chance of having the proper orientation. If we remove some of the reactants, so there's less probability of finding the correct orientation between the two reactants, so therefore this will decrease the rate of the reaction. Adding a catalyst, we just spoke about, this will lower the activation energy, so therefore you need less energy to reach the transition state for products to occur. Therefore, this will increase the reaction rate. Question D, this coincides with the temperature. If we place the reaction flask in ice, this will lower the temperature, and therefore the molecules will move slower. Therefore, it will decrease the rate of the reaction. And increasing the concentration, we just saw the formula in the previous slide. The numerator will increase, the amounts of reactant increase as well. Therefore, there will have a higher chance of getting the correct orientation to reach our transition state and get our product. So for E, it would be increase. Let's look at a particular example here. We have CO, 2 carbon monoxides plus oxygen gas gives us 2 carbon dioxides. What happens if we raise the temperature? Well, the molecules will move faster and have a greater ability to come together and therefore give us our product. This will increase the reaction rate. If we remove some O2, there's a less chance of the reactants coming together with the proper orientation. So this will decrease, and adding a catalyst again will lower the activation energy barrier and therefore increase the reaction rate. So the second topic is chemical equilibrium. We start off with saying a reversible reaction is a reaction that proceeds in both directions, towards the right and towards the left. This is represented by a double arrow. And I would say all reactions, even for instance when we dissociate strong acids, HCl going to, for instance, if we have HCl, breaking down to H plus and Cl minus, even though this is a strong dissociation, we still have a little bit of reaction going backwards. So we have a little arrow going to the left. But we just focus and assume that the double arrow means that the reaction goes forward and backwards. So when it reaches equilibrium, meaning that the forward reaction, the rate of the forward reaction equals to the rate of the reverse reaction, we have a state of equilibrium. And this will happen over time. So look at this example. If dinitrogen tetraoxide reacting to give NO2, nitrogen dioxide. We have here, if we put this NO2, this N2O4 in a beaker, at time 0, we have a lot of N2O4, and over time, it's going to react to give us our NO2. So it reacts to give us NO2 is slowly going to decrease. Conversely, if we look at the side from the NO2 at the very beginning, we don't have any in our beaker, but over time it's going to increase. It's going to start forming, and eventually it will level off the concentration. So at this point here, from here moving to the right, the rate of the reaction going forward equals to the rate of the reaction going backwards, the reverse reaction. So this point here I'm going to circle. So the rates are equal, but not necessarily the concentrations. Looking at our example, you still have a little bit more N2O4 than you do at NO2 at equilibrium. So the rates are equal, but not necessarily the concentration. And from here to the right, we have equilibrium that is formed. This is the same diagram that I showed in the previous slide. We have concentration versus time. And just wanted to show you, once the concentration starts leveling off, once it doesn't increase or decrease, we say we are at equilibrium. So here is all equilibrium. So this can happen in seconds, this can happen in days. It depends on the equation. But yes, usually equilibrium is established over time. So here's an example. Write the forward reaction and reverse reaction of the following. So the forward reaction is going from left to right, which is written here down below. And the reverse reaction is the opposite, going from right to left. So I wrote down the products, now they become the reactants. The CS2 becomes a reactant, and we get a reverse reaction here on the bottom. So let's fill out the sentences here. Reactants form products in the forward reaction. If we're going forward, you're going to reactants give products. And when at equilibrium, the reactant concentration doesn't change. If you guys saw in the graph, you get a flat line once equilibrium is reached. And the third question, at equilibrium, the rate of the forward reaction should be equal to the rate of the reverse reaction. There are some factors that affect the chemical equilibrium. So let's look at this example here. We have yellow and blue, or we can just call them arbitrarily Y and B, gives us a product of AB. It actually should be YB, so let me switch that. Erase this here. It should be YB as our product. Notice the color, yellow plus blue gives us green. So in this case, we have if the concentration is one of the factors. So what happens is, a typical question you'll see in the lab, you put Y and B in a beaker, and over time it forms an equilibrium. So once the equilibrium is reached, the question will be, what happens if we increase the concentration of the reactants? Well, if we increase the concentration of the reactants, we say the equilibrium will shift to the right. Meaning that we increase the concentrations of Y and B after equilibrium is established, the reaction will try to compensate and shift to the right to make more product. You can also say if at equilibrium we added some YB, what would happen to the shift? What would happen to the equilibrium? It would shift to the left. If we decreased some B, once we reached equilibrium, the reaction will compensate and shift to the left. One of the second factor is temperature. So here we have Y plus B gives us YB plus energy. You don't necessarily look at it as a product being energy. The energy is throughout the reaction, but you can, in terms of writing it down, you can think of it in that way. So for the above reaction, if the temperature of the reaction is increased, the equilibrium will shift to the left to compensate. meaning if you add energy to the system, how will the reaction compensate? It's going to shift to the left because we have extra energy on the left. It's going to shift to the left to give us more Y and B, Y plus B. The third one is pressure, which is also related to volume, as you'll see in the ideal gas chapter. So for the above reaction, if the pressure is increased, the reaction will compensate by shifting to the right. And why is that? So if we have, let's just first establish, we have two molecules here versus one molecule on the right. So what happens if we increase the pressure? The volume gets smaller. We want the reaction to compensate for having a more confined space. And what's going to happen is we have more molecules on the left. Therefore, the reaction will shift to the right so that we have less molecules in the given space. So I'll repeat. So if we increase the pressure, the reaction is going to get smaller. And what's going to happen is we want to reduce the size, the amount of the molecules. Therefore, the reaction will shift right. So that now that we have less Y and B, and we have more YB. Change that to a Y. So the three factors are pressure, temperature, and concentration. So let's look at this following example. This is a photosynthesis, if you recall, from biology. Which way will the equilibrium shift as a result of decreasing the concentration of water? So if we remove some water at equilibrium, this should be at equilibrium. If we remove some water, the reaction will compensate and shift to the left to make up for that lost water. So it should be a shift to the left. If we increase the temperature, here, it's going to shift to the right because we have extra energy on the left side. And the last one, if we decrease the pressure, it's going to shift to the left. If we decrease the temperature, we increase the volume. We decrease the the pressure, we have more molecules on the left side, 12 molecules on the left side versus 7. It's going to shift to the left to compensate for that. It's going to make more molecules. Also, you'll also touch this also in the acid-base section, but we'll introduce here. If we want to write an equilibrium constant, we call this Kc. So if we want to express a constant for this reaction, we would take the products, the concentration of the products, divided by the concentration of the reactants. You can get a bit more complex if we have, for instance, a 2 in front here, then there would be a 2 up here, squared, but we won't, I don't think you'll be touching this in the chapter, but the products divided by reactants will give us an equilibrium constant. It'll give us a number. And if the equilibrium constant expression is greater than 1, it favors the products. If the equilibrium constant is less than 1, it favors the reactants. And if the equilibrium constant equals to 1, you are at equilibrium. So this is an example. We have NaOH dissociating to Na plus and OH minus. This is our equilibrium expression. Products divided by reactants. And we also be wary that our states, aqueous again means AQ, liquid is for L, aqueous and aqueous. We don't write liquids or solids in our equilibrium expression. So normally we would have the H2O here, but consider it's a liquid, actually has a value of 1. We can just omit it from the expression.